AP Physics students, this is Mr. Everly. I'm off to Jenison today, can't be with you, but here's a quick video that basically rounds up all the information you need at the end of Chapter 10. Last time, we quickly defined what torque was as a cross product of moment arm, R, and force F. We drew the strange potato picture, drill a hole in it, put a pin through it, and apply a force. R represents the moment arm, the distance from the pivot point to the point of application of the force. When we calculate the torque, what we want is to break the force down into two components, parallel and perpendicular to R. The angle between R and F is, if you extend R out and take a look at the angle between that direction, the direction of R and the direction of F, that's theta. So this is F cosine theta, and this is F sine theta. Remember, we discard the component that's parallel to R, and we take up the component that is perpendicular to it, and we say that the magnitude of the torque is equal to the magnitude of R times the magnitude of the force times the sine of the angle between them. All right. Our first example is kind of an easy one. A weekend plumber, unable to loosen a pipe fitting, slips a piece of scrap pipe, sometimes called a cheater, over his wrench handle. He then applies his full weight to the end of the cheater by standing on it. The distance from the center of the fitting to the point where the weight acts is 0.8 meters, and the wrench handle and the cheater make an angle of 19 degrees with the horizontal. Find the magnitude and direction of the torque he applies about the center of the pipe fitting. All right, so let's say here is the pipe fitting. He puts a wrench on it. Wrench is too short, so he adds a piece of pipe. He applies his weight to it in this direction, and that's our force of 900 newtons. Okay? R is always from the pivot point to the point of application of the force. Now they tell us that the angle between the wrench and the horizontal is 19 degrees. So I'm going to say the angle is 19 degrees and R is 0.80 meters. So if I want to calculate this torque, I'm going to say, look, the magnitude of the torque is going to be 0.80 meters times a force of 900 newtons times, kind of ran out of room here, times the sine of the angle between the direction of the force and the direction of the radius. Now here's R, and what I do is I just continue R. It kind of points off in this direction. Therefore the angle that we want, theta, is that right there. Now this angle here is 19 degrees. So this angle is 19, this is 90, this angle here is a total of 109 degrees. So it's important to get the angle between the direction of R and the direction of F. In this case, it's not 19 degrees, but 109. So if we perform the calculation, it turns out that the answer is 680 Newton meters. Okay, and the way I've drawn the picture, R cross F, using the right-hand rule, putting your fingers in the direction of R and crossing them, curling them in the direction of F, we get a torque vector into the page. But in any case, the magnitude of the torque is 680 Newton meters. All right, the next part of this is the second law of motion for rotation. Now, we all know that the first law of motion is F equals ma. I beg your pardon. The second law of motion, that for linear motion, is F equals ma. So if we look at this great divide thing, we think, well, force is the thing that causes linear acceleration. Torque is the thing that causes rotational acceleration. Linear inertia is mass. Rotational inertia is this crazy I thing that we've been defining over the past couple days. Now, I'll give you an example. Suppose that we have a single particle, fixed point, maybe a string holding the particle so it can move in a circular path about this point. If I want to accelerate it rotationally, I might apply a force on it in this direction. There's R. If I apply a force on it, for instantaneously, it's got an acceleration that way. And the relationship between the force and the acceleration would come from F equals ma, m being the mass of the particle. So, well, if we say there's a tangential force on this thing, then that tangential force equals mass times acceleration. But we could also think of this as being a torque. So the torque on this thing would be R times F of t. Okay? But we could replace F of t with ma. And if this torque creates a rotational acceleration, an acceleration in this direction, we can think of this as being acceleration equals alpha times r, because by the definition of radian measure, we know that alpha equals a over r, where a is a tangential acceleration. So if I make that substitution, I've got r times a times alpha r, or mr squared times alpha. Now we know the rotational inertia of a single particle going in a circle is mr squared, so I could change this to I alpha. So in general, the sum of the torques on an object equals the rotational inertia times the angular acceleration. So this gives us the second law of motion for rotation. In fact, sometimes we put the heart around that one and call this the rotating heart of physics. Okay, a couple of examples. A cable is wrapped several times around a uniform solid cylinder that can rotate about an axis. The cylinder has a diameter of 0.12 meters and a mass of 50 kilograms. The cable is pulled without stretching or slipping with a force of 9 newtons. What is the angular acceleration of the cylinder? So what we'll have here is a cylinder looking into the page here. This is the end of the cylinder. We wrap a cord around it many times, and we put a force on it which will cause the cylinder to rotate. The radius, r, is 0.12 meters. The mass of the cylinder, 50 kilograms. Massive cylinder. The force being applied tangentially to the cylinder, 9 newtons. Okay. The angular acceleration of the cylinder we could find if we realize that there's actually a torque on the cylinder as we attempt to cause it to rotate by pulling on the string. So actually, if I draw my r this way, which is totally acceptable, we can see that r is perpendicular to f. So we'll use t equals I alpha. We'll say, all right, the only torque on this thing is r times f. The rotational inertia of a cylinder is 1/2 mr squared. And see if we could calculate what alpha is. Okay, so first thing we do is y out a r, multiply both sides by 2, divide both sides by m, and the remaining r, and we have the angular acceleration. So 2 times 9 newtons, divide by 50 kilograms, times 0.12 meters. We get an answer of 6.0 radians per second squared. Okay, so the magnitude of the acceleration, 6 radians per second squared. As I drew the thing, the acceleration is going to be r cross f, which is into the page. So if I put my fingers in the direction of r, curl them into the direction of f, the way I drew this thing anyway, the acceleration would be into the page. Another example. This one's kind of interesting because it combines an acceleration that's linear and an acceleration that's rotational. So the question is, find the acceleration of the mass m, this guy, and the angular acceleration of the cylinder of mass big M and radius r. Now the thing to keep in mind here is that the acceleration of this mass and the angular acceleration of the cylinder are linked because it's being caused by the string that's wrapped around the cylinder and continuous with the string that's attached to the mass. So if this mass accelerates, then the outside edge has the same linear or tangential acceleration. So we could say, look, alpha is related to this acceleration of the mass through the definition of the radian. So this bridge equation, alpha equals a over r, will be very important. All right, so the mass here has 2 forces on it. It's the tension in the string and its own weight. Okay, now because we have an acceleration this way, what we're trying to find, an acceleration downward we're trying to find, I'm going to break tradition a bit and say that downward is positive and upward is negative. And hopefully in a minute you'll see why I'm doing this. So if I do an F equals ma on the hanging mass, I'm going to say that mg minus ft equals ma. Okay. Next, I'm going to take a look at the rotating cylinder. The rotating cylinder has a radius r, mass m, and to figure out its acceleration, we'll say sum of torque equals I alpha. The only torque on this thing is this force here, which is also the tension in the string, times the radius. So I'm going to say r times f of t equals the rotational inertia of this cylinder, which is 1/2 mr squared, times alpha. Okay? If we do a little y action, we notice that the tension causing this rotational acceleration is equal to 1/2 mr alpha. Now, if we look at our equation here, we know that A equals r times alpha. So this r times alpha here is the linear acceleration of our cylinder. So I'm going to say f of t equals 1/2 ma. So the tension in the string would have to be equal to 1/2 the mass of the pulley times this acceleration, the tangential acceleration of the pulley. So if that's the case, we can bring this back to our F equals ma and say mg minus 1/2 the mass of the pulley times the acceleration equals ma. So in other words, we can bring what's true over here about the tension in the string over to here when we're talking about the tension of the string on the mass. What makes this possible are two things. We know that the tension pulling up on this mass is equal to the tension pulling down on the pulley. That's assuming a massless string or a very, very low mass string. We also know that the tangential acceleration of the pulley is related to the linear acceleration of the block. So now we can solve for A by putting all terms containing A over to one side. And factoring out an A. And dividing. All right, so we have an expression for the acceleration of the block and also the tangential acceleration of the cylinder. If we want the angular acceleration of the cylinder, all we have to do is take this value and multiply by r. So we know that alpha, I beg your pardon, we have to divide by r, I apologize. We know that alpha is a over r, so that means alpha in this case is equal to mg divided by r times the quantity m plus 1/2 m. Okay, that's it for now. As you work on these problems, just keep in mind that if we're talking about a linear acceleration, that requires a linear force. So F equals ma, we've got linear inertia, basically, as mass. On the other side of things, we've got torque, which is a radius or moment arm crossed with a force is equal to a rotational inertia or moment of inertia times a rotational acceleration. So very similar principles. The sum of all the torques on something is equal to its rotational inertia times its rotational acceleration. As you read through the book, these are sections 10-8 and 10-9. So I would take a look at the book and see some of the examples and see how they develop some of those equations. What I'd also like you to do is to read section 10-10 on work and rotational kinetic energy. Back when we did work, we said work was the integral of, I beg your pardon, that was kind of silly. Work is the integral of f dx, integrated from x naught to x final. We're going to find also on this side of things, when you apply a torque to something, to spin it up, to get it to move faster, you're also doing work. Work still equals change in kinetic energy, so we can still use that. And the definition of work on the torque side is that work is the integral of torque d theta, from theta initial to theta final. So where on this side we're applying a force to something to move it a linear distance, here we're applying a torque to something to rotate it a angular distance. Okay, just like over here, power is dw dt, power is dw dt. Whereas here we can kind of play with it and say, hey, power is force dotted with velocity. Same deal over here, power, instantaneous power, is torque dotted with rotational velocity. So again, the analogy from linear to rotational is pretty complete. Take a look at the problems. Remember, I have my solutions online on the Moodle page. I'll come back on Friday to help you out with any problems that you have difficulty with. I'll see you folks later.